This is Lab9 spring in 2 dimensions. The main objective is to analyze and track a spring in motion in 2 dimensions and calculate the corresponding change in the potential energy of the spring. By making the system include the spring, the work done is equal to 0. From that, there must be a potential energy of the spring included in the energy principle calculations, which results in a delta potential energy of the spring of negative 0.000726. These are the parameters I set when doing tracker to track the motion of the ball on the spring. This is the tracker video that we were given to analyze. You can see how the ball is moving in both X and Y directions. The delta T is 1/10 of a second. And you can see that the spring forms an oscillating motion. This is the computational equations we used. We needed to calculate L hat, the force of the spring, which is negative Ks S L hat. F net includes F gravity and the force of the spring. We also found the kinetic energy, which is 1/2 mass of the ball times velocity squared. Then we had to find the potential energy of gravity, which is the mgh, and h in this case is the displacement of the y. We also calculated the potential energy of the spring, which is 1/2 Ks S squared. K was calculated from our tracker data. This is a model of the spring and how the yellow ball represents the computational spring and the blue is the data inputted from the tracker video. You can see how the blue ball lags a little bit behind the computational model. They follow the same path, just something is off with the timing of their movement. This is a graph of the X values. The graph at the top is from tracker. We plotted the X against the change in time. The lower picture is the experimental data projected onto the computational data. You can see how they mirror the motion. However, the peaks are like not half, but like 1/10 of a second off, which we saw as the blue and yellow ball moved in the computational model. We did the same for the Y values. You can see the same results. This is the change in spring potential. It's not uniform, but it's necessary to assume that the work done is equal to 0. So what does it mean? Compare the period of oscillation you found from examining the X component of position with the period of oscillation determined from the Y component of position. The X has a larger displacement, so that means that the Y it has a larger displacement than the Y does, so the X oscillation period has a faster period than the Y, so they are not the same. With your new choice of system, determine the work done by the surroundings. Is the energy principle satisfied? When we add the spring into the new system, we can assume that work equals 0, and therefore the energy principle is satisfied. How does changing the location of the origin change the physics of the system? The Y position is amplified while the X positions remain the same. We see this by changing it we changed the origin from 0 to negative 0.7. And you can clearly see that the yellow and blue ball do not match up because the yellow has a much more amplified Y displacement.